The objective of this video is to practice using the Maxwell stress tensor to calculate force and torque on electric machinery. We've previously introduced the Maxwell stress tensor and come up with expressions for the normal and tangential force density on the surface of our rotor. We're now going to practice using this in a couple examples to calculate the total torque and force on our rotor. And for this machine, we're going to be assuming that we have a slotless stator with an air gap field of 0.9 Teslas that's distributed sinusoidally in our air gap, and a linear current density on the inner bore of our stator with a peak of 40 kiloamps per meter. So I'll sketch what this looks like now. And you'll see that I'm labeling the coordinate system that we're using, where we've got x coordinate going to the right and the y-axis going vertically. And we're going to define the angle alpha as being the angle moving off of the x-axis in the counterclockwise direction. This happens to be the direction of the unit vector phi in the cylindrical system. And so if we go back to the problem definition, we've said that we have this linear current density of 40 kiloamps per meter on the inner bore of our stator. And when we say this, we mean that this is acting in the z-hat direction. So z-hat is coming out of the page at us. And we can try to sketch this, noting that on the x-axis, alpha is equal to 0. So sine of 0 is 0, so there's no current there. But moving counterclockwise from that, we start to get a positive current density coming out of the page at us. I'm going to draw these as our conductor symbols, and I'll use the size to indicate the magnitude of the current. So as we get further and further away from the x-axis, we get larger and larger currents until we get to the y-axis, which is where we have a peak positive current coming out of the page. And similarly, moving down from the x-axis, we have current going into the page, which I'm drawing little circles with x's in the middle. And they're getting larger in magnitude as we get further away from the x-axis until we get to negative 90 degrees, in which case the sine of negative 90 is a negative 1. And this repeats itself as we get to the other side. Okay, so we've drawn our linear current density, and just for completeness, we'll label the top as our stator. So this is the problem geometry, and we need a little bit more information. We're going to assume that we have a rotor diameter and a certain rotor length. And so our first question is, calculate the torque that is produced on the shaft. Let's just talk for a second about nomenclature and sign convention for torque. Torque is equal to R crossed with F. R is the vector that points to the location that our force is acting, and F is the force vector that is acting on our surface. This is the definition of force, that's equal to radius crossed with our force vector. Force is going to be positive in the counterclockwise direction for us. This is the same thing as saying in the tangential direction or the phi-hat direction. And so just from the definition of what a cross product is, that means that torque is going to be a vector in the z-hat direction coming out of the page at us, and it will be positive for a positive value of f. Or stated a different way, a positive torque is going to tend to accelerate our rotor in the counterclockwise direction. So we've now talked about the sign of our torque and force expressions. Now let's go back fundamentally to what torque is and how we can relate it to the results of our previous video on the Maxwell stress tensor. And we were able to express our Maxwell stress tensor as this vector sigma of force pressures acting on the surface of our rotor. And these pressures were either in the normal or tangential direction. So to calculate torque, we're going to integrate the r vector, the radius vector, crossed with our pressure vector, and the only component of the pressure vector that will survive this cross product is in the tangential direction. And last time we showed how to set this up where our radius and our axial length of our rotor come outside of the integral, and we're able to integrate just over 0 to 2 pi of the angular location on the rotor's surface. So the question now is, what is our expression for our tangential force density? And going back to our previous lecture, we see that we have this expression, 1 over mu naught times our normal flux density times our tangential flux density. Let's first talk about what our normal flux density is. Now, I told you in the problem statement that we have this air gap field, B delta of alpha, of 0.9 teslas times the sine of alpha. And in general, when somebody tells you that the air gap field is a certain value, they mean the radial component or the normal component of the air gap field. So we can interpret this expression to give us an expression for Bn of alpha, where Bn hat is a 0.9 Tesla. Okay, so we know what Bn of alpha is. How about B tan of alpha? So recall from a previous video where we set up our boundary conditions that we can relate B tan of alpha to the linear current density on the surface of our iron. So in that previous video, we considered this case right here. And we had drawn an Amperian loop that we use to determine conditions on our tangential current or our tangential fields. And our conclusion was that Bx in the x direction in the air is equal to mu naught times our current density at that location. And so we can interpret this to tell us that what the tangential component of B is at some angle. So we're going from considering this at a linear position, we're going from linear coordinates to cylindrical coordinates, as being the negative of mu naught times our linear current density. So why is it negative? Well, if you map this diagram up to our air gap up here, you can see that our tangential components, they are in the phi hat direction. Whereas in this diagram down here, x, the x direction, if we mapped it up to the surface of above, if we considered this iron region here to be our stator, the x-coordinate in this linear diagram is clearly in the negative phi hat direction. So that's how we get this negative mu naught times A of alpha. And this is a quick hand-wavy explanation, but I encourage you to sit down and work this out yourself. In fact, you can prove this result by considering a simple Amperian loop like this in cylindrical coordinates on the surface of your stator and rotor, and you'll come to this conclusion. If you do it right, you'll come to this conclusion right here. Okay, so we now have an expression for B tan of alpha. It's going to be negative mu naught times A of alpha. And we can plug this expression for our tangential force density into our torque integral. We'll take this and we'll plug it in up here. And we can work on this integral. Until we get this torque expression. And now we can calculate our torque. We'll notice that r was the radius of our cylinder, which is in fact our rotor, and we can relate that back to the rotor diameter that we were given up here. And we finally get our torque expression. And we can note that torque is negative. That means that our torque is acting in the clockwise direction. That is, it's going to tend to make our rotor accelerate in the clockwise direction or rotate in the clockwise direction. The next part of this problem, we're going to suppose that the rotor is rotating at a speed of 1,450 revolutions per minute in the counterclockwise direction. And then we're going to calculate the electric power. We know that power is equal to torque times our rotational speed in radians per second. And again, torque is positive in the counterclockwise direction, and the same is true of radians per second of our angular speed. And we can determine our angular speed in radians per second by doing a unit conversion of our speed in revolutions per minute. And we find that we have 151.8 radians per second. Now we're in a position to calculate our power. And since our rotational speed was given to us as a positive value, that means that our angular speed, omega, is also a positive value, and the shaft is rotating in the counterclockwise direction, while the torque is being applied in the clockwise direction. All of this translates to a negative power, and in this case we have a negative power of 34.3 kilowatt. And what does it mean that our power is negative? It means that we're operating as a generator. If torque was being applied in the same direction as rotation, we'd be operating as a motor. We'd be transferring energy from electricity to mechanical. So we'd be going from electric to mechanical power as a motor. But as a generator, we're going from mechanical to electric power. Next, we're going to compare the maximum observed shear force density to the maximum observed normal pressure density or normal stress density. And remember, we're representing shear as sigma F tan. And since we're talking about the maximum or the peak, we'll put a hat on it. So the peak tangential shear, the peak tangential stress density is the shear. And the normal force density is sigma Fn. And since it's the peak, we'll put a hat on that as well. So we already have an expression for sigma F tan of alpha. And the maximum of sine squared is 1. So therefore, the maximum value of this is going to be Bn hat times A hat. That's our peak tangential force density. And if we plug in the numbers for this, we get 36 kilopascals. And so I express this in kilopascals. A single pascal is in units of newtons per meter squared. Now let's do the same thing, but for our normal pressure. And going back to our previous lecture, we get the following expression for our normal force pressure density. We already have expressions for our normal flux density and our tangential flux density. And so we can pull the sine squared term out to get our peak normal pressure. And so when we plug in these terms, we see that we have two contributors to our normal pressure density, and that is our air gap field, or our normal field, and the second is our tangential field, which is due to that circumferential current density. But that second term contributes nearly nothing to our normal force density. This is approximately 0 compared to the normal term. 1 kilopascal compared to 322 kilopascal is nothing. And so what's often done in electric machine calculations of normal forces is that you neglect this second term up here. And that would be this term over here. So finally, we get a value of about 322 kilopascals for our peak normal pressure density. And so if you compare these two, we notice that the force density in the normal direction is approximately an order of magnitude larger than our shear force density, which is an interesting result. It shows us that the electric machine is actually far better at creating radial forces or normal forces than it is at creating rotational torque. So for this example, the peak normal force pressure is 1 order of magnitude larger than the peak shear. And however, the key difference here is that if we were to consider the average normal forces acting on our shaft, we would get 0 newtons of force in the x and y direction, but we have clearly an average shear acting on our shaft that gives us this 226 newtons of torque. And for this reason, it's very important that you keep your machine centered, that you keep your rotor centered, because if it becomes slightly uncentered, you can see that you have a potential for a very large force to develop on your rotor. Okay, that was our first example of using the Maxwell stress tensor for torque and force calculations. Let's now consider another example. And in this case, we're going to just consider 2 block plates of iron. And we're going to assume that there is a magnetic field in the air gap between these plates, which has a normal value of 1.5 Tesla. So there's 1.5 Tesla traveling in the normal direction, that is from the top of the bottom plate towards the bottom of the top plate, and that there is 0 tangential field. Your assignment is to calculate the force that is acting on the top surface of the bottom plate. We're going to assume that the cross-sectional area of the top surface and the bottom plate is 10 centimeters squared. And we're going to assume that the fields are uniform within that air gap. So please try this on your own. Press pause and press play when you are ready to watch me work the problem. So copying down our expression for our normal force density, we note that we have no tangential field, so this can simplify considerably to just being bn squared over 2 mu naught. And this is kind of a classic expression. You'll see this all the time when considering the normal force density on the surface of a material, that you either assume that there's no tangential fields or you have no tangential fields, so it's just bn squared over 2 times mu naught. And remember, this is a pressure density, and in this problem we can plug in our value for bn and get 895 kilopascals acting on that surface, pulling it towards the top plate. And so we can find the total force by integrating over the area of the bottom plate. However, in this case, we've said that the fields are uniform, so we can just multiply sigma Fn times our area. And we have to do a unit conversion from 10 centimeters squared to meters squared. And we arrive at this answer of 895 newtons are acting on the top surface of the bottom plate, pulling it towards the top plate. So this concludes our lecture. In this video, we have practiced using the Maxwell stress tensor to calculate force and torque on electric machinery. We worked through a very detailed example of a force calculation on a slotless stator with a linear surface current density on the inner bore of the stator. This is kind of a fictitious situation. In later lectures, we're going to work toward why we can make this modeling assumption and what it means. So we calculated the force, the torque acting on the rotor. We converted that to a power. We noted that it was a generator. And then we made this interesting observation that despite the fact that we designed machines to produce torque, they actually are subject to very large normal forces on the surface of the rotor. And these normal forces typically are an order of magnitude or larger than the shear forces that are used to produce torque. And then finally, we worked a simple example where you had a chance to try your hand at using the Maxwell stress tensor to calculate forces on an object.